My name is John Mitchell. I'm a product manager with Intrepid Control Systems, and in this video I'm going to review the core file analysis functions that make up our data mining framework that we call integrated post-analysis. There's a Git repo for all the files related to this framework posted at this link here. And in the repo there is a Word document that describes how to set up your PC with Visual Studio Code and Python so that you can follow along with this example. There are a number of different example Python scripts that use the framework for doing various types of data mining, and the idea is that you can go through the examples on your PC and learn how the framework works and then tweak the scripts to apply them to your own data. In order to use the framework on your PC, you have to have our data plotting tool, DataSpy, installed on your PC. And the installer for that program, the path for it is shown here. And when you download the installer, you have to unzip it, and this is the password to unzip the installer on your PC. I have DataSpy running here, and I have the example data file that's included with DataSpy loaded into my plot window. I have 5 signals plotted, which you can see in the legend. And I'm showing the individual data points from each signal here by turning on this one feature. And you can tell from looking at the spacing of the points that each of the channels was logged at a different rate. And in DataSpy, you can click on a signal in the plot in the legend, and then you can step from record to record on that signal using the arrow keys. And so right now I have trans output speed as the active signal, and I'm stepping from point to point in trans output speed. And I can also pick turbine speed and then step from point to point on turbine speed. And the reason I'm showing this is the data mining framework is kind of analogous to the legend in DataSpy, because there's a virtual cursor that you can place anywhere in the file, and then there's an array of doubles that has the value of all the signals at the cursor. So you can open a file with IPA and specify what signals you care about, and then you can position this cursor in the file and it'll automatically update the values of those signals at the cursor. And you can also activate signals, more than one signal, and then step through the exact records on that signal, just like you do in DataSpy. And the way the legend works in DataSpy is it shows you the value for each signal that most recently precedes your cursor. So the cursor only has one current timestamp that it's at, and the values that are displayed are the values that are the closest to it, but that precede it. It doesn't look ahead or interpolate. And that's the same way that the IPA framework works. So during this review, I will be switching back and forth between Visual Studio Code and DataSpy just to show you how this aspect of the library works. Okay, I have Visual Studio Code running here. Let's start by opening the folder that corresponds with the sample file functions script. Go File, Open Folder, and then pick the folder Demo IPA File Analysis Functions. Then if you click on this top link here, Explorer, this allows you to look at all the files that are in this folder. And all of the example scripts associated with the IPA library have a file that's called __main __.py. And this is a common convention in Python. This file shows the entry point for execution of the whole project. So it just points to the main execution file that's in the project. And that file is called Demo IPA File Analysis Functions. And just like all the other examples, at the top of the main execution file, there are several comments. There's an overview of what the script does. There's a list of the inputs to the script and a list of the outputs to the script. This particular script does not have any outputs. It's merely designed to exercise the various file I/O functions that are included with the library. And down at the bottom, it shows a description of all the different functions that are used in this example. But I'm not going to go through the comments too much here because I want to actually run them in this example. So if you look at lines 77 through 85, these are a bunch of import statements. And one of the great things about Python is there's an incredibly wide range of library functions to do all sorts of things in Python. Many of these libraries are included with the install of Python, and some are not. NumPy is a very popular Python library that's not included with the install of Python. And like the setup instructions describe, you can install NumPy into your Python environment by just typing pip install NumPy at the command line. Lines 87 through 89, these are imports from, the first two lines are imports from the ICS IPA library. This is actually part of the file IO framework. There's a main object data file IO library, and then there's the IPA interface library. These are two things that you pull in. And then there's also a SIG enum file that is actually in this project. So we're importing the SIG class from the SIG enum file. And if you look at it really quickly, you'll just see this is an enumeration. Python doesn't have enumerations for some reason, and you can simulate one by just making a class that has initial values that count up. Okay, so then starting at line 92, there's a function definition. This function is called set time basis signals, and it takes two arguments. The arguments are a list of signals in the config file and a list of time basis signals. And I'm not going to talk too much about this until we actually run it, because it's easier to understand when you actually see it used. Lines 107 through 115 set up a runtime logging tool that will write text to a file called ipa.log, and they'll put a timestamp with every time there's a line written to the file. It'll be timestamped, and you can click on the example here, IPA log. This is from previous executions of the demo. Every line that's written to the log has a timestamp and then whatever text is written. And this uses the logging class, which I've imported from Python. And if you have these same lines of code in the top of all the Python files in the project, any one of them can write to the log file by just typing log info and then whatever text you want. It's a handy way to keep track of what's going on in your program, mainly for use in debugging. Okay, so let's set a breakpoint on line 21 by just left clicking next to 121, and then we'll hit F5 to run this script. So it stopped at this line, and now I'm going to press F10 to step over this, and it'll call this get config file. So in this case, it asks you for the config file, and just go to the examples folder where the demo file analysis functions are, and every one of our scripts has a config file associated with it, and the config files have the extension ASL. So just select that config file and say open, and then the next line will request some input data files. So let's step over that, and now let's pick the example file that's included with DataSpy. Now these functions, get config file and get input file list, they work differently if you're running this script on the wireless server versus in the PC. In the PC, they show you file open dialogues to pick the files. On the server returns a list of file paths for these two functions. So these functions work differently depending on what mode you're running the script in. So the next two lines are going to open the config file and then write the contents of the config file to a variable called config. And the config variable is a dictionary in Python. A dictionary works a lot like a JSON file, and it's really kind of like the contents of a JSON stored into a variable at runtime. And one of the things about Python is it really makes it convenient to use these dictionaries and store them as JSON files. I hadn't used a JSON file or a dictionary prior to working with Python. It's a powerful tool, and it's an important part about learning Python. I'm not going to go into too many details, but I do have the config variable in the watch window on the left. If you can't see the watch window, you just click on this bug here on the lower left of the display menu, and it shows the watch window. And you can copy variables like this script channels, for example. You can copy that, just double click in the watch window and Control V, paste it in there. And right now it says name error because I haven't run this line of code yet. Python does not require that you declare variables before you use them. It's some advantages and disadvantages of doing that. MATLAB is similar to that. So if I hit F10, it'll step over that line, and now you'll see the script channels got updated with a real number. And you can click the arrow to see what is in the script channels. And also, with likewise with the config file, you can see what's in the config file. If you look at the config file, you can see that it's a JSON file, and it has just two keys. One is signal list for use in time basis, and one is channels. And both of these keys are in the config dictionary, but they are represented a little differently in the dictionary. The next line of code is written Pythonically, I would say, in that it uses the unique syntax of Python. Line 134 is actually a for loop where we're looping through all of the channels in the script channels and assigning the name and script element from each of the channels to this signal list. So all of this is done in one line, which Python programmers will applaud that you packed all that code into one line. But for me, it's hard to read if you're not very familiar with Python. So I tend to not be a very Pythonic programmer, but I just wanted to point out that's one of the unique aspects of Python. So this next command, I'm not going to go into it. We use this function called set time basis signals, and I'm just going to show what the output is. So let's step over it. And the output of it is a string, and the string has a 1 and then 5 zeros after it. And the number of characters in this string is always equal to the number of channels in the channels list. So there's 5 channels in the channels list, and that's why there's 5 characters in this string. The reason that the first digit is 1 is that in the config file, the one signal that is in the time basis list, trans output speed, is also the first signal in the channels list. So that 1 means that trans output speed is used for time basis, and all the other zeros mean that the other signals are not. So now we're going to enter this loop here where we will call this loop once for every file that's among the list of files. In this case, I only picked one file, so I'm just going to step through this. And then I'm entering a try statement, where this is just, it's often good when you're opening and closing files that you put those inside of a try block so that if there's some problem with the file, you can exit execution gracefully. You can see that the except is at the same level of indentation as try, so that if any one of the files fails, it'll just go on to the next file. So one of the other unique things about Python is the nesting of various loops are defined merely with the tabs. There's no braces or semicolons or anything required. It's all in the number of tabs that you have that shows the way that the different loops are nested. So now at line 145, we are actually going to take the config file and the data file, and we're going to instantiate an ICS data file object using this statement, ICS data file. and we're going to call it data. So let's step over that line. And now the framework library is opening the data file and the config file and setting up the current record and the virtual cursor, and it's calling it data. That's what's happening. And now I'm calling this set active mask string, where I have that string with the 1 and 0s in it. And again, I'm not even going to really go through that right now. It'll be a little clearer further on. Okay, now I'm at line 148, and I'm about to call this function jump before timestamp. And the argument that I'm giving it is 0. And the jump before timestamp function, it places the virtual time cursor wherever you specify in the file by time in seconds. So if I pass it a value of 0, it'll move the cursor to the first record in the file. So I'm just going to step over that, and current timestamp is now 0.26079. And if you go to DataSpy, you'll see that the first record for trans output speed has a timestamp of 0.26079. That's why the current timestamp, after calling this jump before timestamp, is set to that time, because trans output speed is the one signal that we have set active. Okay, now we're going to call this function getPoints. And what getPoints does is it gets the array of values at the virtual cursor. So if you look in the watch window, I have each signal's index displayed here. So I have the trans output speed index in data points, the turbine speed, engine speed, pedal position, and engine state variable, all shown in here. They all have a value of 0 except for the engine state variable, which has a value of 8. So if you go to DataSpy, the first value of all the signals, it has a value of 0 except for the engine state variable, which has a value of 8. It actually shows 9 here. It's because the enumeration is it's 0 based. So my only point is that at this point, data points is like the value at cursor 1, and the location of cursor 1 is this current timestamp. So that's what these two functions do. Now this next function, get timestamps, it will show you the exact timestamps for each one of the signals that are in the array of values. So as I mentioned, all of these signals have different time vectors. So if you want to know what is the exact time that goes along with each one of these signals, you can reference it by looking at the timestamps. Okay, so now at line 170, I'm entering this while loop. And in this while loop, I'm going to just step through each record in the file. And there's 3 different sections in this nested if where I manipulate the signals that are used for time basis, and I also try some of the different get next record functions that are available. So I'm just going to step through this line by line, and right now my current timestamp is still 0.2607. So as you can see from the way this code is written, I'm just going to keep on calling get next record each time. And notice the timestamps. Right now I'm at 0.3105. If I go back to DataSpy and I click on trans output speed and I hit the right arrow, you can see the third record in the file has a timestamp of 0.31053. And that's what is happening. Since I have trans output speed set as the active mask, each time I call get next record, it'll move to the next record for trans output speed. So now it's 0.3355. Go back to DataSpy and look at the next record. It's 0.3355. So the values of all the signals is not very interesting right now because they're all 0. But you'll see as we progress that it always shows you the values at the cursor. So now I'm going to just keep stepping until I get beyond 0.5 on my timestamp. It's about 25 milliseconds per loop. Okay, now I'm at 0.51. So now I'll enter the second set of if conditions. If my timestamp is between 0.5 and 0.7, now I'm going to set my active time basis signals to turbine speed and output speed. So I set this time basis list, and then I call this function to get the string, which now it's 11000. So it's 11000 in this case because trans output speed is the first signal, trans turbine speed is the second signal, and all the others are not active. So that's how that works. And I only do the set active mask once. That's why I use this flag first loop after next time range. So now I'm going to call get next record. And now the current timestamp has moved to 0.51307. So if I go back to DataSpy and I click on turbine speed and I go to the next record. Oh, I got to go beyond 0.5. 0.51307. That is an exact timestamp for trans turbine speed. 0.51307. So if you look back here, that's where the cursor is. But now turbine speed and output speed are both active. So when I call get next record, again, it's going to move to the next exact timestamp for either trans turbine speed or trans output speed. So I go to the next record, and now my timestamp is 0.5257. So I go to the next record, and the next record is 0.5257. And notice that point is a trans turbine speed point. I'm still between points on my trans output speed. So go to the next record. Now I'm at 0.53557. And it looks like the next point is going to be trans output speed. And that's my 0.53557. So you see, since I have trans output speed and turbine speed active, it is stepping from to anytime either one of those signals is updated. And the reason this is important is if you were doing some math that involved both turbine speed and output speed, you would want to check your math anytime there was a new value for either of those signals. I mean, you may want to. If the signals aren't changing that quickly, maybe you don't care. Oftentimes, you could just pick one signal as your time basis signal and you can blast through the whole file. But if you really want precise calculations on all the signals, you can use this active mask to control how frequently it checks your array. And it allows you to balance the execution time with the fidelity that you need on the analysis. So now this will keep looping until I get to 0.7 in the timestamp. So I'm just going to set a breakpoint here, and I'm going to get to the next section where it's after 0.7. So I'm going to hit the continue button. Now it stops, and I'm after the 0.7. My current timestamp is 0.7008, and I still have turbine and output speed active. I'm just going to go to DataSpy, and I'm going to change this to 0.65 so that I could see the data at 0.7. And I'll pick a trans output speed and just get to the nearest point there. So yeah, now my current timestamp is 0.7008. So that corresponds to this point, 0.7008. So you can see that is the closest point after 0.7 is the first turbine speed point after 0.7, which is at a timestamp of 0.7008. So anyways, that's just showing you how that works. And now what I'm going to do is I'm going to call this jump. I'm going to call jump before timestamp again, but I'm going to jump all the way to 5 seconds into the file. So I call that once, and now my timestamp is 4.9922. So it's moved the cursor to the closest exact point that precedes 5 seconds into the file, which is 4.99. So now I'm going to go here to 4.75. And so 4.99, it looks like that's going to be turbine speed point. So 4.99224. 4.99224. So that's where it's jumped to the active cursor to the closest actual record to 5. And again, the values of the cursor haven't changed yet because the data is really static at this point. So now I'm going to call this get next changed record. So as you can see so far in this file, the values have not done anything. They haven't changed. They've been constant. So there's not much need to step through each record. So get next change record, what it does is it'll move the cursor to the next time that any one of the signals has a different value. And in this case, it checks all the signals, but only at the exact timestamps for trans turbine speed and output speed. So if any one of the signals change at those points, it will stop the cursor there. So now I've moved the cursor to 17.9799. So I've skipped over 13 seconds of data in the file. So let's go back to DataSpy, and I'm going to go to 17.75. And you can see from the plot that the signal's values are actually starting to change. And the first signal that's changed here is engine speed. But again, I am still only moving along the times for turbine speed and output speed. And the engine speed went from 0 to a value of 108.9. So if I go back to here, I can see that engine speed is 108.9 and my time is at 17.9799. So 9799, that's just showing you there how. So now when I call get next record, it'll jump from only among the records where one of the values has changed. So this allows you to step over stagnant data in the file. So frequently you could use one signal as your time basis and step through get next change record. That could be a real fast way to blast through if you're looking for something really simple. But even records that haven't changed, there's some value knowing that there was actually an update that did not change. So these base functions allow you to jump around through the file and look at the values of the signals and not have to deal with buffering all the different time vectors and mixing them together. So that's the basis of the core file analysis functions of IPA.